Sequences and series are very similarly related. Sequence is simply just a list of numbers, and a series is simply taking that list and adding them together. Okay. Several different types. So today, basically what we learn in this course is stuff you've already talked about. I just talked to Mrs. Coles, and she said in Algebra 1 we have a Ohio State standard. Okay, the state of Ohio says you need in Algebra 1 to deal with arithmetic and geometric sequences. You guys remember hearing those words?
Yes.
Okay. Guess what you have to do in Algebra 2 as a standard? Arithmetic and geometric sequences. And guess what happens that's really nice in college algebra is you learn them again, right? Okay, so you have a little bit of a foundation. So I'm not saying that everybody's going to be great at this, but we do have a little bit of background. Okay, we're going to talk about those four things hopefully today. Kind of give you kind of the overall structure for just general sequences. And general sequences can be, there's so many different types of sequences in regards to the patterns that show up. When I use the word arithmetic, that means it's a type of sequence, a category of sequences that shows a particular similar pattern. Okay, geometric sequences are kind of the same way. When you get to calculus, you'll talk about things called like Taylor series. Okay, and they show they're basically a sequence that we're adding together that shows a similar pattern to other Taylor series sequences or series. Does that make sense? So we're going to kind of talk about just general sequences in today's lecture, but then on Monday and Tuesday, kind of narrow our focus on geometric and arithmetic sequences. Okay, those two types. I think what gets people in trouble for the most part in sequences and series is the notation. Okay, we start using subscripts and it confuses people. What I want you guys to understand is that when I write the terms of a sequence, okay, obviously the terms in this sequence here are 5, 10, 15, 20, 25, and you can see the patterns, probably going to go 30, 35, 40, 45, 50, whatever. But if I don't want to talk about the particular number in the sequence or the object in the sequence, but I want to talk about its location. So if I look at like number 20, okay, or the value of 20 right here, okay, we would say that that is the fourth object in the sequence, right? Or the fourth object in our list, okay? So we call that A sub 4, okay? The 4 referring to the location of that object in our list. So we've got A sub 1, A sub 2, A sub 3, A sub 4, A sub 5. Whether I care about what the numbers that are in those positions or not, the subscript tells me what the position is. Does that make sense to everybody? Okay. So if I say A sub n is the nth location. And then n is maybe a number that we just come up with on our own. Say, okay, maybe I want n to be 12. So now when I say A sub n and n is 12, it's really the 12th position. Or if I say A sub n, I want n to be 100, now I'm saying it's the 100th position. And I want to know then what is that value sitting in that 100th position. Is it okay? Okay. Now our rules a lot of times, okay, are formulas that allow us to develop these numbers, 5, 10, 15, 20, 25. A lot of times, most of the time, they are predicated off of that n value. Okay? They're predicated off the position that the object is in the list. So right here, n would be 1. Does that kind of make sense? Okay? Here, n would be 2. Here, n would be 3. N would be 4. N would be 5. Okay, and I keep going. I go n, 6, 7, so forth. And they ask you, can you come up with a rule? Well, if I look at this list, the sequence of values, okay, if I take my n and multiply it by 5, do I get that number right there? If I take this n and multiply it by 5, do I get that number right there? Okay? If I take that n and multiply it by 5, do I get that number right there? And I can see that that happens with the remaining two terms in the sequence that they defined for me, right? So that tells me, okay, kind of through induction, kind of through that pattern, that tells me that my rule for this is probably A sub n equals 5 times n, where n is the position in my list. Okay? Does that make sense to everybody? What's nice about that, if I want to know the 100th term, and I didn't have a formula, I'd have to write out 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, all the way up until I've written 100 things, right? But now if I've got a formula, and I want to know what the 100th term is, okay, I take 5 times 100, and it gives me 500. Does that make sense, everybody? Okay. So it's going to be useful in regards to kind of projecting nth terms to have a formula. All right. Now, as we see a couple examples today, coming up with that formula, sometimes very difficult. Okay. And sometimes there's not a set one way of doing it. There's not a set these are the steps that I walk through every single time I see a sequence to come up with the formula. Okay. Because it just doesn't happen that way. Okay. Some sequences you might. If we go by definition, a sequence is just a list of numbers. There may not be a pattern. Does that make sense? Okay. So developing the rule is usually difficult for people. Okay. What is nice though, and this is what we'll talk about on Monday and Tuesday, is that sometimes when you're given a sequence, you can recognize that there's a particular type of pattern. Like that last one was a particular pattern. 2, 4, 6, 8 pattern. 3, 6, 9, 12 pattern, right? Okay, when I see things like that, those are arithmetic, okay? Which would be really nice to be able to deal with, okay? And so we'll investigate what it means to be arithmetic. And if I recognize that my sequence is showing that behavior, then we have a set standard way of coming up with the rule for an arithmetic sequence. Does that make sense, everyone? Okay. This is just another way of saying kind of what we've already said. A sequence is a function A whose domain is the set of natural numbers. All they're saying here is that when you have this list of values, it's simply just a bunch of output values that you have received from some rule. So 5, 10, 15, 20, 25, 30, those are my output values from the rule or from the function 5n. Where my input values, my domain values, were n equals 1, n equals 2, n equals 3, which are our natural numbers. Okay? So that's how we define a sequence. And in here you see them using kind of the function notation. Okay? They're saying if A, let me see if I can write it this way. Kind of writing here like if A sub n is like equal to 5n, then A sub 1 would give me my 5, A of 2 would give me my 10, A of 3 would give me my 15. Does that kind of make sense to everybody? Okay. Now, you might like that notation, which is fine because we're pretty comfortable and familiar with functions. However, just generally speaking, they never use that format. Okay? We use the subscript. So instead of saying A of 1, A of 2, A of 3, A of n, we say A sub 1, A sub 2, A sub 3, all the way through A sub n. Is that okay with everybody? Okay. Key thing to remember is that subscript is telling you the position in the list. Okay. All right. So we see some examples here, and you see that it doesn't have to be A sub n. You see C sub n, you see T sub n, you see R sub n. The two that I like to use are A and T. Okay. A just because most textbooks use that. T because it reminds me of term. Okay. So first term, second term, third term, that kind of thing. Does that make sense, everybody? But use whatever letter you want to identify the objects in your list. And then they usually do use a subscript of n. But you can use anything you want to. It could be M, it could be R, okay? It could be S, but it's really hard to say the S term, okay? Or W, it's hard to say the Wth term. Doesn't flow as well as nth term does. So that's why they use N. If they ask you, because you're going to see this in your homework, they're going to ask you to find the first X amount of terms. Okay? In this case, find the first 5 terms. So all we're doing here is we're going to say, okay, here's my rule. So if I want to find the first term, A sub 1, that value of 1, your subscript, is the n that you're going to plug into the rule. So 2 times 1 minus 1 would give me 1, right? A sub 2. Okay, now n becomes 2. So you get 2 times 2 is 4, minus 1 gives me 3. A sub 3. Now n is 3, so I get 2 times 3 is 6, minus 1 is 5. And we can, do we need to do 4 or 5? Does that kind of make sense what we're doing here? Now if they wanted the 100th term, what's nice is that we got the rule. So if I do want the 100th term, this is usually what they ask you to do. Do a couple that are in order, like 1, 2, 3, 4, and then do one that's really far away. And you guys start to see the convenience and the niceness, I guess, of having it for me. So if I go n to be 100, now I get 199, right? But if I didn't have the rule, you can start to see, as you would do like a sub 4, I'll just do it real quick, would give me 7, right? A sub 5 would give me 9. And you start to see that this is actually what we call an arithmetic sequence, because the common difference is 2 being added to every previous term, right? If I didn't have this rule, if that thing didn't exist, or I didn't have the ability to come up with it, and I want to find the 100th term, well, then I need to know the 99th term, don't I? And if I want to know the 99th term, then I need to know the 98th term. If I want to know the 98th term, I need to know the 97th term, right? So if I want to find a to the 100th without a rule, I have to write out 100 terms. If I want to know a to the 1000, I've got to write out 999 terms. None of us probably want to do that, right? So that's the convenience of being able to develop the formula. Even though the work involved in developing the formula might be difficult, it's a lot less difficult in regards to time consumption than writing out a list of 999 terms. Okay, we can go through and do a couple of these other ones. I want to do part D here, okay, because it incorporates a unique term that is pretty useful in recognizing what happens in a sequence. So I'm going to talk about this one here. We're going to do R, it's this one, R sub n. So let's say R of 1. Okay? So if I got R of 1, I'm going to have negative 1 raised to the first power over 2 to the first, right? So what's that give me back? Negative 1/2. Then we're going to do R sub 2. And I get negative 1 squared over 2 squared, and that gives me back 1/4. I'll do R sub 3, so we get negative 1 cubed, and then 2 cubed, so it gives me negative 1 over 8. R to the 4th gives me positive 1 over 16. And then R to the 5th, I'm just going to go ahead and recognize the pattern here, negative 1 over 32. So my list then, if I write it in list format, or sometimes called an array, negative 1/2, 1/4, negative 1/8, 1/16, negative 1/32, okay? And that thing is infinite in regards to its length, so it keeps going. So I put those ellipses to show the pattern continues infinitely in that direction. What are you seeing happening from term to term? Think about this. If this thing wasn't there, if I just had the numerator as 1 to the nth, would my numerator always be 1? Yeah, and then all my numbers would be positive numbers, right? But because I have that negative 1 to the nth, do you see how it's allowing you to kind of bounce back and forth between negative and positive results? Okay. The term that is allowing that to happen, the term that allows you to oscillate from the one term being positive, the next one being negative, the next one being positive, the next one being negative, is that negative 1 raised to the nth power. Okay? And the reason I talked about that is because in the next slide, we're going to see an example where they give us the list and they want us to come up with the rule. Well, the list oscillates back and forth between plus and minus. So if that happens, you'll always need a -1 to the end. That kind of makes sense to everybody? Okay. Now think about this. What if I wanted my list, instead of starting at, because we had -1/2 to 1/4 to -1/8 to positive 1/16. What if I wanted it to start at positive 1/2, then go to -1/4, then go to positive 1/8, and then a -1/16? What if that's what I wanted to happen? Well, how would I have to adjust this to do that? Think about this list. If this is a -1/2, how could I get it to go to 1/2? If this is positive 1/4, how do I get that to go to -1/4? Multiply by a -1. So I would need another negative here, and that would provide that list there. Does that make sense? So you might see in a rule some weird, I call them tools. I think that -1 to end is a tool that allows us to bounce back and forth between plus and minus. And you might see the opposite of -1 to the end, okay? Which is another tool that allows you to bounce back and forth between positives and negatives. Determine on what you want to start with, whether you want to start with a positive number or a negative number. Does that kind of make sense? Okay. On your final, it's not going to be a question on your final, but it is something to think about when you're dealing with sequences in general. They don't always have to be solely positive numbers. Okay. So we see here that we're eventually getting to. Well, let's look at this first. We write this first set of terms out, right? And we see 1, 3, 5, 7, 9. So these are the last slide, just kind of all worked out for us. We see 1, 3, 5, 7, 9, and then we go out to the 100th term and get 199. If I go out to the 200th term, the 400th term, the 1000th term, what do you think is going to happen with that 199? Is it going to get smaller or bigger? It's getting bigger, right? Okay. Will there ever be kind of a limit to it? No, there's no boundary to that nth term's amount. Okay, so this thing is what we say to be divergent. Okay, when a sequence or a series is not approaching some finite value, okay, we say that the sequence is divergent. Okay, going off in kind of separate direction. You think about the word diverge, it means that they're not going to meet, right? Okay, so that list, those values in the list are not going to meet some limit, some boundary. Okay, same idea here. N squared minus 1. You know, the larger n gets, the larger each one of these values gets, right? Okay, but look at these next two. I got 1/2, and then I go to 2/3, I go to 3/4, 4/5, 5/6, and then I go all the way up to 100 over 101. Okay. And then if n is, let's say n is 1,000, I have 1,000 over 1,001. Are those numbers getting closer and closer to something? Getting closer and closer to 1, aren't they? Okay. So when we see that a list of values is approaching some limit, some boundary, some finite value, in this case that's approaching 1. Will we ever get there? No. But we're approaching it. Does that make sense? We say then that is a convergent sequence. Okay? Is that doable? If we look at that bottom one, part D, okay, because we're oscillating back and forth, we're kind of all over the place here. We have issue on whether saying that's divergent or convergent, because this is going to be, you know, we do. What happens if we're to plot these things? So a -1/2 would be here, and then, so for our first term, so -1/2 there, and then like -1/4. So you bounce back and forth on opposite sides and get closer and closer to the x-axis, right? Okay. So that is the idea that we would be maybe converging to 0. Does that make sense? Okay. So those are questions that maybe we're interested in. We'll talk a lot more about that when we get into arithmetic, and specifically when we get into geometric sequences. We're really interested in geometric sequences converge or diverge. These are asking you to come up with a rule, okay? And there's not a pattern that is really easy to recognize with these two examples. Like on Monday and Tuesday when we talk about arithmetic sequences, there's going to be a really easy pattern to recognize, okay? With the 5, 10, 15, 20, 25 example, that was a really easy pattern to recognize, right? If I look at that top one, there's not a really easy pattern to recognize, okay? And the more examples you see, the better you're going to get at this stuff. And you're going to say, well, how do you know? How did you know to look at it and do it this way? I've seen them a lot, and I know kind of the ins and outs of a lot of different types of sequences and how they're developed, and just use that knowledge and manipulate the current sequence to come up with a rule. What I look at here is I recognize, looking at all my numerators, what kind of numbers are those? Odd numbers. Look at all your denominators. What are those? Even numbers. Okay? Now, usually when you write a sequence, you're going to need to know n. Okay? So, n here would be 1, right? N there would be 2. N there would be 3. And n there would be 4, right? How could I take the n value in each one of those positions to get my denominators? Multiply by 2. Take this n, multiply by 2, you get that? Take this n of 2, you multiply by 2, you get 4? 3 times 2 gives you 6. 4 times 2 gives you 8, right? So you're seeing that your denominator is probably 2 times n. If you're going to take a number theory course, and hopefully you took Algebra 1, so you know this, that every even number is defined as 2 times n. Okay? Take any n value you want, even, odd, or whatever, multiply it by 2, what do you always get back? You always get an even number back, don't you? Okay? So that's what we're getting there, the denominator is 2n. Okay, so if I take 2 times n, and I'm always going to get an even number back, how do I get an odd number back? What do I need to do to 2n so I get an odd number back? Subtract 1, right? You're going to add 1, that's going to give you an odd number back as well, right? Okay, but if I add 1, think about this. If I add 1 to this, okay, am I going to get that number right there? No, okay? If I subtract 1 from that, I do get that, right? If I subtract 1 from 2n, I get that, right? Okay? So we're seeing here that if I subtract each one of these denominators, if I subtract 1 from each denominator, I get my numerator, right? 4 minus 1 gives me 3, 6 minus 1 gives me 5, 8 minus 1 gives me 7. So if my denominator is 2n, subtract 1 from 2n, and now I have my numerator, okay? Now, there's not, and hopefully you see in that example, there's not a predefined way that we approach that, okay? The next sequence we see may or may not use anything similar to that approach. Does that make sense? Okay? So what's nice is that when we first deal with sequences, try to analyze them and see if they do follow kind of a general pattern of maybe being arithmetic or being geometric, which we'll talk about obviously next week. That next one, okay? Still using the n values. So here, I'm going to write n equals, in this case, 1. That case will be 2. There's 3. There's 4. There's 5, right? How can I get, just whatever comes to mind first. How can I get, don't even worry about the negative sign, okay? Because you see how they alternate, right? Negative, positive, negative, positive, negative, positive. So when we're done, we're going to make sure that we add that tool that we've already talked about into our formula to get to oscillate back and forth. So what I do when I see these sequences like this, 2, 4, 8, 16, 32, I don't look at the plus or minus. Because I know there's something we can adjust that or with at the end, okay? Let's look at the 2, 4, 8, 16, 32. And what comes to mind? What can I do with this 1 to get 2? Multiply by 2, right? That may be the first thing that comes to mind. And see if that then continues through the rest of the pattern. If I take 2 and multiply by 2, do I get that? Okay, so right now I'm thinking 2 times n will give me my numbers on my list, right? I get to this one. If I take 3 times 2, do I get that? No. Okay? So even though 2 times n worked for the first 2 terms, it doesn't work for all of them, so that's not my option. Okay? But we do see that in each one of those, there is something to do with 2's in each one of those terms, right? Can I rewrite this as, and this is just kind of as I've seen a lot of these in my past, I know that if I can't use multiplication, the next thing I'm going to try to do is look at powers. Okay? I take powers of 2. It's 2 to the first, 2 to that end. Does that give me 2? There's 2 to that end. Does that give me 4? There's 2 to the third, which is that end. Does that give me 8? There's 2 to the fourth, give me 16. And there's 2 to the fifth, give me 32. Okay? So there we're seeing that 2 to the nth is the ultimate rule. That's going to give me 2, 4, 8, 16, 32, right? Nothing similar to the way we first approached that first sequence, okay? So the approaches here are a little bit different, okay? But they alternate in sign, right? So if they alternate in sign, what do I need to incorporate? That thing right there will always allow it to alternate in sign, okay? Now there might be other ways of doing this, okay, and writing it, but that's I think the best thing to think about in regards to when they oscillate back and forth between plus or minuses, when you're trying to come up with a rule, don't even worry about the plus or minus. See how you can create those quantities, and then know that the negative 1 in, when you multiply that in, that will take care of the plus or minus. Is that doable? Okay. There may be, I think, negative, if I take negative 2 to the nth, does that provide the same exact list? Okay, negative 2 to the first gives me negative 2, right? Negative 2 squared, now we're squaring the negative. Does that give me 4? Negative 2 to the third, cubing the negative, does that give me negative 8? So we see that these two things are equivalent, so either one of those would work. I just like the one with the negative 1 at the end. Okay, it's just, I know it's uglier, it's maybe more cumbersome, but I think that's the one that you're going to see probably most of the time in a textbook. All right, so the reason I show that is for you to kind of gain an appreciation for the ability to first recognize what type of pattern you might be seeing in your numbers, okay, in your sequence. So on Monday, when we see 2, 4, 6, 8, that's that's arithmetic. That's going to be really nice to deal with. Or when I see 1/2, 1/4, 1/8, and I recognize, oh, well, that's geometric. That's going to be really nice to deal with. I have a predefined set of steps to come up with a rule for that sequence. These two may or may not follow either of those patterns, and coming up with a rule might be a little bit more difficult. Okay. Also, if I asked you guys to come up with a sequence, and you just write a bunch of numbers down with commas between them, did you come up with a sequence? Yeah. Okay. Your sequence is, by definition, a sequence is just a list of numbers, right? Okay. So it may or may not even have a rule that we're able to easily determine. Okay. Let's just kind of walking through the results for those last two. All right, recursively defined sequences, and this is, after we talk about this, is where we'll stop today. A recursively defined sequence, if you remember back to Algebra 1, Algebra 2, basically what that means is that your nth term is predicated or based off the previous terms. Okay? There's a famous sequence Anybody know what that sequence is?
Fibonacci sequence.
That's the Fibonacci sequence. Okay. Fibonacci came up with that or analyzed that. If you've ever watched Da Vinci Code, yeah, a big part of that movie. What I really like about sequences and series is that there's a lot of things in nature that occur in regards to sequences and series. And one thing that I think is like really interesting, if you were to look at how like pine cones or sunflowers kind of position their seeds, obviously their goal is to reproduce and get as many seeds as possible inside a sunflower, right? That's kind of the biological idea or goal of sunflower is to reproduce as many times as it can. So it wants to maximize the area inside the sunflower's kind of blossom or whatever. So the way that if you've ever looked at a sunflower, they kind of spiral, right? When you see the seeds inside the sunflower, the way they spiral, if you were to count them, they spiral in a Fibonacci sequence, okay? If you were to look at a tree, and not every tree is exactly the same and is going to follow this, but a lot of trees, when you have your trunk and you start to look at the branches that come off that trunk, okay, and they start positioning themselves around that trunk in a three-dimensional kind of space, a lot of times if you start counting those, they're in the sequence, the Fibonacci sequence to one another. Which is pretty, I think that's pretty interesting that just takes over in nature, and that's a sequence that we deal with algebraically, but we can see it used elsewhere or expressed elsewhere in biology. But what happens with the Fibonacci sequence? What are we doing here to get each of these terms?
You take the first two numbers and then add it together to get the third term.
Right, so I take those two numbers and it gives me that term there, right? And then I move one spot down the list and I'll take those two to get that one, right? And then I move down the list again and I'll take those two add together to get that one, right? Okay? So what happens here, if I just call this, let's call that A sub 1, A sub 2, A sub 3, A sub 4. Let's say I wanted to find A sub 4. A sub 4 is going to be, so this 3 came from adding what things together? There's those two, right? Okay, so A sub 4 was basically adding together the blue stuff I circled, right? So A sub 4 is equal to A sub 2 plus A sub 3. If I look at A sub 5, okay, A sub 5 would be that one. It's adding together 3 and 4, right? A3 and A4. So A plus 3 plus A sub 4. A sub 6 would be A sub 5, or sorry, A sub 4 plus A sub 5. It's addition, so the commutative property could work if you wanted to. I was trying to write this in a pattern. So I keep going through and finding A sub 7, A sub 8, A sub 9, and so forth, right? Eventually getting to A sub n. Let's see if we can write a rule here, okay? If I look at this number right here, how does that 6 and that 5 relate? Or how does that 5 and that 4 relate? Or how does that 4 and that 3 relate? They differ by what? 1, right? Okay. The number on the right, these numbers here, those subscripts, all differ by 1 from these numbers on the left-hand side of the equation. So, if it's n, wouldn't this be A sub n?
Pardon the interruption, but this is just an announcement that the prom committee meeting for today has been canceled. Again, the prom committee meeting for today has been canceled. You will be notified of the rescheduled date when that is rescheduled. Thank you.
Now, how does that number relate to that one? And how does that one relate to that one? And how does that one relate to that one? These numbers are all what compared to those numbers? Yeah, they're one less, right? So they're one less than what we've got here. So it would be A sub n minus 1, right? Well, what's A sub n minus 1 minus 1? A sub n minus 2. Okay? So that is that's the Fibonacci sequence. That's the rule for the Fibonacci sequence, okay? Now with the Fibonacci, we have to tell then what is the first and second terms. So we have to start off knowing that our first two terms are those. Sometimes you might see this Fibonacci sequence start off with a 0, 1, instead of just 1, 1. But you have to give me somewhere to start, because if I just give you the first term as 1, then you can't find the one before that, right? That makes sense? So you need two terms here. But it's referred to as recursive because we're using previously defined terms to come up with the next one. What stinks about this, if I want to come up with the 100th term, what two terms do I need to do that? 98, 99, right? But if I want the 99th term, I need the 97th and 98th, right? If I want the 98th, I need the 96th and the 97th. So if I want to go out to some nth term, I've got to write that list out that many times. There's really no algebra right now with that real neat, cute algebra that's going to allow us to find the nth term without writing the entire list out. Okay. Sometimes with recursive defined sequences, you can do a little manipulation to get you that nth term, but in this case, we can't do that. Just real quick, guys, if you see in your homework the word partial sum, all they mean by partial sum is that you're adding up that many terms of your sequence. So if they want the, let's say I've got this sequence here, and they want the third partial sum, all that means is add that number, and that number together. Add the first three. If they want the fourth partial sum, add the first number, the second number, the third number, and the fourth number together. Does that make sense? Okay? So whenever you see partial sum, it's just adding that many of the first n terms together. Okay? We'll do a little bit of that with arithmetic and geometric sequences, a little bit more on Monday and Tuesday. There's actually formulas for arithmetic and geometric partial sums that are pretty easy to deal with. That allows me to say I want to find the 100th partial sum, but I don't need all 100 terms to do that, okay? Because of the pattern that we know exists in the arithmetic sequence or geometric sequence. So that's kind of what we're going through with next Monday and Tuesday. Hopefully then that will be enough information.